is the third session on properties of a pure substance, and we will continue from where we left off yesterday, which was we were looking at the properties and we started discussing what is an ideal gas. So we had looked at the properties of vapors, and we said that the equation of state, which we are so familiar with, PV equal to RT, this doesn't apply to the vapor states, and this applies only to an ideal gas. And this is the simplest form of the equation of state. We call it, let's say, EOS, where we have P is equal to RT upon V. So basically, we have expressed pressure as a function of, say, specific volume and temperature, or rho and temperature. The reason for putting this form up is that we'll see in a minute that as we start deviating from ideal gas behavior, this equation will get modified. And essentially, it will remain something like this, but with lot more additions and modifications to make it fit the experimental data much better. So we'll come across many different types of equations of states, and each one of them has their own advantages and disadvantages. But remember that all these are for an ideal gas only. So last time what we had seen is that we had defined the reduced temperature TR, T upon T critical, and we defined reduced pressure as the pressure upon the critical pressure. The reason we did that is that it gave us a uniform set of parameters that are independent of the material, and so in some way these reduced properties, these are some sort of what we call a normalized on a known constant, and we can then talk in terms of different materials having same reduced temperatures behaving in a similar way. So we defined these two, and turns out that these are the critical states are the properties of the substance, and along with that we have other critical states like the critical state specific volume, the specific entropy, the specific enthalpy, specific internal energy, and so on. For a given substance, all these are unique, and you can just look up any tables and we can pick up all these numbers from there. So this is what we defined, and then we went about doing an exercise of saying that if we plot this side the reduced pressure and this side the y-axis, we plot the compressibility factor, then what will the graphs look like? For that we defined yesterday the compressibility factor Z as PV actual divided by RT, or is a ratio of the actual specific volume of the material divided by the specific volume that would be calculated from the ideal gas equation state. What basically we are saying though is that when we talk of V ideal gas equation of state, this lower part, if you have any pressure, any temperature for a material, nothing stops us from saying that I will calculate V as RT upon T. But the question is, this is from the ideal gas assumption, and the question is, how good is this assumption? And that is what if this ratio tells us, that we measure something in the laboratory divided by what the ideal gas equation of state tells us, and we get the compressibility factor Z. And we went about drawing this curve and saying that ideally if z is equal to 1 and this is 1.0, this is 0, and this is a logarithmic scale going from 0.01 reduced pressure to say 0.1, 1, and say 10, and even further than to 100. And we argued yesterday that at very low pressures, when we start plotting, we say, well, at a certain reduced temperature, what is the Z? We start getting one problem. We say, well, okay, now at this reduced pressure and another the same reduced temperature, what do I get? That's the point. At this and the same reduced temperature, we get this. So like that, if we go about doing plots, we'll get a series of points. They start looking something like this. This would be at some particular value of reduced temperature. At some other value of reduced temperature, it begins to look like that. In some cases, it goes like that and then goes up. So around here, not at 1, but something like more than 10, we see that Z becomes much greater than 1. Whereas on this side, Z is less than 1. That means as pressures remain low and temperatures keep increasing, the strength of Z, which is divergence from ideal gas behavior, increases, and Z more than 1 means that V actual is greater than V ideal gas. This is when Z is greater than 1. If Z is less than 1, it means that this is less than this. So V actual is less than what V ideal gas. That means actually the material, the density would be the opposite. So you can look at it that way, that here density is less than the ideal gas prediction, and here it is opposite. So in one case, the molecules are actually closer than what ideal gas predicts. In the other case, they are further apart than what the ideal gas equation predicts. That's what these two are telling us. This complicates life quite a bit. Because what has happened now is that the nice equation of state that we had, PV equal to RT, has now to be changed, and we have to modify this as P is equal to Z times RT upon V. And Z, as you can see here, this is a function of reduced pressure and reduced temperature. Or for a substance, it is a function of pressure and temperature. If you take reduced pressure and reduced temperature, you get a common graph, which I will show you in a minute. So how do we get this? And that equation for Z, this is what, again, one has to do curve fitting, and it comes out with a big long equation. Okay, so before that, let's look at how this curve actually looks like. Okay, so this is the real graph with real data from substances, and here is what you see on this picture. In the legend, it says there's data for methane, ethylene, ethane, propane, butane, isopentane, N-heptane, nitrogen, carbon dioxide, and water. So we took the real data, measurements, calculated Z, and plotted these. And you can see, so let's take the first curve at the top here, this one, and you can see that there are some points that are there. There are these circles which are there, triangles which are there, some crosses which are there, and then they all fall within a relatively narrow band through which a curve fit has been done. The same thing was done with reduced temperature of 1.3, and we get this sort of a fit. And at reduced temperature of 1, that means temperature is equal to critical temperature. We get all these points here, and then they go off here. They all fall on one line. And this axis for reduced pressure is a linear axis, and Z is also a linear axis. And the maximum here is reduced temperature of 2, which means we are twice greater than the critical temperature. So this is the reason why the generalized compressibility chart, as this is known, is so nice. That irrespective of what materials we were looking at, and there are so many of them here, all their properties can be described by one family of equations, which is based on reduced pressure and reduced temperature. So that's what we have here. The same picture on another scale. Okay, this is the same data, but now what has been done is a curve fit was done to that data, and the model is called the Lee-Kessler simple fluid compressibility chart. So there's a Lee-Kessler equation of state, which was based on the data fit. And once we have got an equation, we can put as many points as we want and generate nice continuous curves. And that is what you see on this picture here. So the x-axis is reduced pressure on the logarithmic scale, 0.01, 0.11, 10. And on the y-axis is the compressibility factor from 0 to 1, and they're actually going up to 1.3 over there. And for all substances, the critical value of the compressibility factor turns out to be 0.29. And here are the curves. The topmost curve, which is very close, this is the line z equal to 1. This is the one. So if we are close to this line, ideal gas behavior is pretty much good. And so let's look at this first line here. Reduced temperature is 5. And what we see is this line goes up there. And it stays very close to 1, almost all the way through. And then slightly goes up. And then after this, the diagram is not given, but they all rise very sharply after this. So at reduced temperature of 5, that means 5 times greater than the critical temperature. At up to, like for this case, reduced pressure up to 1, that means you are pretty close to the critical pressure. The compressibility factor is very close to unity. And that's quite a nice thing to know. But what if you are at not that high a temperature? That's the next line. Here you see reduced temperature equal to 2, and the line comes like this. Now it is pretty much close to 1 up to this point, which is reduced pressure 0.1. After that it decreases, reaches the minimum, and then again goes up. And then there is a big change between 2 and 1. This is 1.05, 1.1, 1.2, 1.3, and 1.5. At reduced temperature 1.5, again all the curves start here, but at 1.5 it goes down there and then again rises up there. So now the deviation, if you see here, this is about 0.8, Z 0.8. So you are 20% off from what ideal gas equation tells us, and for most calculations that is not acceptable. We want to be within maybe 1%, 2% of the true value. We can never be exact. That's the real world. Then there's 1.2. It dips, the minimum here dips further down. We are down very close, just about 0.5, 0.55, something like 0.53, something here. So it stays below at 1, about 0.1, and then drops very drastically. And then with pressure increases a lot and again goes up there. And at 1, it comes down there and then goes up. So if you look at this part, they all start converging towards 1. So if you go to even lower reduced pressures, all these curves will come very close to 1. And that tells us that as long as you have a vapor, then if pressures are reduced pressures are less than 0.1, then at any reduced temperature, the substance will behave like an ideal gas. That's one nice criteria to have. The second criteria is that if TR is relatively high, between 2 and 5, say like that, then even at reduced pressures up to almost like maybe 1 or even maybe 2, we can say that there is ideal gas behavior at these temperatures. So there are two things that emerge here, that we have two nice conditions, that reduced pressure less than 0.1 and definitely less than 0.01, any reduced temperature, the vapor phase will behave like an ideal gas. The liquid phase will of course not be anywhere like an ideal gas. So what you're seeing here below is this line, which is the saturated liquid state. So as I mentioned, any pressure and temperature we can always calculate the specific volume, but the real specific volume in the liquid is going to be several orders of magnitude different from that, and so you see compressibility factors of all below 0.1, 0.1, 0.2, something like that. And these are lines of constant dryness fraction, constant Z, 0.7, 0.8, 0.85, 0.9. Not constant. This reduced temperature is constant. And because the saturated state at this reduced pressure and this reduced temperature, many states are possible. The saturated liquid state is a very poor as a behavior, has very poor behavior like an ideal gas. It's not an ideal gas at all. Whereas the saturated vapor state is getting close to ideal gas, but within still about like 0.95, so this is about 5% off. But if we come further down, then this difference goes down, and at such low pressures, even the saturated vapor, which is what they call here saturated gas, can be reasonably approximated as an ideal gas. So very low pressures, this would behave like an ideal gas, but not at higher pressures. So this is what this picture tells us in a thing. And yesterday when we were looking at many of the property charts, let's go back and see what would happen to the TS diagram. This is temperature and specific entropy here. And we had talked about in all cases that if we are dealing with a substance or a system or a problem in which there is vapor-like behavior, when we make a property diagram, we must always show the dome. And that's what I'm going to do now, is that on this case, let's say that the dome looks like this. That's the critical point. This is the dry saturated vapor, this is the saturated liquid. And what that compressibility chart just told us is that if you look at constant pressure lines that we had discussed earlier, they'll go off like this, but they're definitely not linear though. That difference here is not the same as this. This is going in a very non-linear fashion. These lines are going up like this, the critical pressure isobar goes like this, and they go up like that. So what compressibility chart told us, that if you are far away from this, that means if you are somewhere here, reduced temperatures are very high, that means this is there and you are much above that. And at low reduced pressures, so remember this is increasing pressure. Okay, so this is increasing pressure. This could be 0.01 megapascal, 1 megapascal, this is 220 megapascal, 300, 400 megapascal. So at low reduced pressures and high temperatures means we are somewhere in this region over here. Something like this. And that's where we say that ideal gas behavior is good. And it also told us that even pressures are very low, then you could even get down in this region and say that in some cases this would also be a reasonably okay type of an ideal gas behavior. So this region and far away from this would qualify for classification as an ideal gas. And so if I have to now shrink this diagram and say, well, where are we dealing with, say in the case of air, where we are looking at many processes, say diesel engine, petrol engine, things like that. This is S, this is T, and for things like nitrogen, oxygen, the saturation dome would be somewhere over there. This temperature being like 120 Kelvin, 150 Kelvin, something like that. And ambient temperature is 300 Kelvin, which means we are in this air that we have around us. Reduced temperature is 2 or of that order, like 2.2 or something more than that. So we are quite high on that. And if you look at pressures here are low, so we are far away. If you look at the constant pressure line over there, these lines would go off there. Ambient air would be, temperature would be somewhere there. So we are looking at this part. And if you look at any process where we heat the air, like say burning fuel in a boiler or in a diesel engine or a petrol engine or in a furnace or compression, in all those cases, temperatures would further rise. So you could say that from 300 Kelvin, we might be going up to as much as 1000 Kelvin. So that would be a line somewhere over there. And pressures, ambient pressure would be say one could be say there, and maximum pressures we deal with many of these applications would be something like that. So we are dealing with a region where many of our applications lie in this zone. And that's nice to know that at the extremes of this, if we check what is the value of Z in each one of them, then it turns out that if all of this Z is very close to 1, it means that any state inside this can be assumed to be an ideal gas state, and any process that happens in this region, for example, say there's a constant pressure heating which is like this, or constant temperature, or constant isentropic expansion which would be like this, say a turbine, gas turbine, aircraft engine, or a compressor which is working, so that would be something like this. So throughout this process, at any instant, Z is equal to 1, which means that throughout the process, ideal gas behavior is fine. And that means that we can do complete analysis of this by just going back to PV is equal to RT. And that's what we do in the first course like this on thermodynamics, that when we look at analysis of cycles like these, we will treat them as ideal gas cycles, use equation of state PV equal to RT, life becomes much more easier, and very quickly we can get a lot of insights into how these systems operate. At a more advanced level, when we go into detailed engineering of these, we'll start relaxing this thing and do many more things to it and get this to be much more realistic. But the first cut analysis that we are looking at is good enough to know what the cycle is and what the basic features are, because that is not going to change. So what does this tell us? That if your cycle is in this region, this part is irrelevant. So what we will be doing now is that whenever we look at a problem in which we say that the substance is always an ideal gas, and we are going to plot this processes and states on a TS diagram, we will not show the saturation dome. So in the diagram, if it is not there and we show a bunch of states like that over there, say, or there, we are implicitly saying that this is an ideal gas state. So if the dome is not there, implies this is a problem involving ideal gases. And if you have a problem where we don't have ideal gas behavior and we want to depict those processes, we must work with this part of the chart, and we have to show the dome as a necessity. So this is a vapor cycle or a vapor process, and far away here is the ideal gas. And in this course, fortunately for us, these two properties are quite different from one another, and so we don't have to worry too much about this. That does not mean that there are no problems where we have both behaviors coming in at the same time. Take, for instance, air, or say nitrogen, which is cooled to produce liquid nitrogen at constant pressure. So that cooling process will follow like this, go there and end up over there. So it started at ambient conditions behaving as an ideal gas. At some point, it said that, well, now you cannot use the ideal gas equation of state, but I still want to know what is the energy transfer in the process. Well, it means that in this type of a problem, we say that, okay, here there is a line, and that line we decide based on what data we have in the property tables. So this line will be decided by the upper limits of the property tables. We calculate changes in properties, say from here to there or there or there, using the tables data. We calculate change in properties from here to there based on ideal gas equation of state, and the total change in the process will be the sum of change in both these. So that's how we will have to handle problems where we know that, okay, somewhere I have ideal gas, somewhere I have a vapor-like behavior or a non-ideal gas behavior, then we must make this distinction. Just assuming ideal gas all the way through is going to be quite a mistake. Okay, so this is the part of this, and now we ask the question that in the vapor table things, the moment I know the state, from the tables we could get all the other properties. And so if we needed to compare S1, S2, or we needed change in specific enthalpy or change in internal energy or any other property, as long as we had two independent properties at the state, we could go to the tables and pick up all the other properties and then do any calculations we want. So that's how we use the tables and charts. Or these days, use a software that is there. And if you don't have a software, you can go online and there are many free things where you just put properties and you will get all the other properties out. So that is what you do here. Here we have two options. One is, of course, we use ideal gas equation of state. That means there are no tables and no charts, which is okay, doesn't matter. The second is there are some tables, but these are largely for a pressure of 0.1 megapascal. So you can say that air or nitrogen or oxygen at 0.1 megapascal, I want to know the enthalpy change from 100 degrees Celsius to 200 degrees Celsius. One can look up this table and get those data. But that is for 0.1 megapascal. For higher pressures, these tables are of no use. At very low pressures also, we can get some idea from this data, but that's not the best thing. So tables are of limited use, and so there are very few tables as far as ideal gas properties go. The best option we have in both cases is that we take the full equation of state, which is a relation between P, V, T, and solve it. That's a much more complicated process. Unless you have to do it, you will do it. Otherwise, we let others do it and we use that formulation for solving our problems. This is what we will do in the tables and charts anyway. That's how these things came about, and so did the software. Here also, we can make tables, but there is no real point because in many cases, this is good enough. So now what we will do is, we say, look, how do I calculate property changes for ideal gases? And we'll concentrate first on change in specific enthalpy, change in specific internal energy, then we look at change in specific entropy, and then we will look at some other things. Okay, so the next thing we have to do, we define two properties. The first is constant pressure specific heat. We denote this by Cp, and it's defined as dH by dt at constant pressure. Okay, so that's what we have. And we can also write this if we want as dH is equal to Cp dt for a constant pressure process. So if H is only a function of temperature, then we can write this as an exact differential, and that's how we get this. The difficulty is that in the real world, this Cp is a very strong function of temperature. And I'll show that data for some substances. So we have two options. Either we assume that this is constant. And in this course, we will assume that. But we should remember that that's only an assumption, and the real thing would be that we integrate Cp with T from state 1 to state 2, whatever the temperatures were. So if you were to do this part and write the full equation, then this is what we will get. dH equal to Cp dt plus a whole bunch of things here. You don't need to worry about it, but I'm showing you how there's a dependence on temperature, how there's a dependence on pressure. The point to note here is that in the square bracket, we have specific volume temperature at constant pressure. So this entire thing is something that can be evaluated from the PVT relationship or the equation of state. And from there, you can do some differentials on it, put it in there, and we can calculate dH from this. So what we do is, we will say that if we define another sub-category within CP, which is zero pressure specific heat at constant pressure. Zero pressure means that the pressure is, say, reduced pressure is very much less than 1, or say 1.2. At that low pressures, it is reasonable to assume that it is constant with temperature, and to denote that it is different from Cp, which is in reality a function of temperature, we use a new symbol which is Cp0. Some books write this as Cp0 over there. Both have the same meaning. So we put that and integrate it, and the relation that we will use in this course is now coming up, which is that H2 minus H1 is Cp0 T2 minus T1. A very nice and a simple equation that is directly related to the temperatures that we are looking at. So that tells us how to evaluate specific enthalpy change between two temperatures. So here, if we needed to know specific enthalpy change from here to here, we just needed the two temperatures, and enthalpy change will be Cp T2 minus T1. And if it was up to the limit to where the tables were, then we could get this number from that equation and the remaining enthalpy change from the tables and add them. The differences are independent of the reference state from which property measurements were beginning. So we are okay with that. So that's one new thing that has come up, the constant pressure specific heat Cp. We'll now look at its counterpart, which is the constant pressure, constant volume specific heat. Or Cv. Cv is defined as du by dt at constant volume. And if we work out the full relation using du is equal to all the expression that we have, we will get this type of a dependence. So basically, we are saying that this is a function of only T and V. So we get an equation on this side, this big bracket term, which is like earlier, a function of pressure, temperature only. So an equation of state will enable us to calculate this whole thing. And if we have to get the exact internal energy change, we integrate this whole equation in some sort of an equation like this, and then get the answer, knowing well that Cv0, like Cp0, is a function of T. So Cv also is a strong function of temperature. That is long and tedious. We won't do that. We will do what we did before with specific enthalpy, and we say that Cv0 is dH by dt, and du by dt, and when you take it to the other side, integrate it, we get the next equation that we can use in our analysis, which is that u2 minus u1 is Cv0 T2 minus T1. And that's a nice compact equation to use for solving problems. So we got two new properties that came out, the specific Cp and Cv, and a sub-classification which is Cp0, Cv0, which is zero pressure properties. And we got now two equations, how to evaluate changes in those properties, and what it tells us is that it is only a function of temperature. The question is, how do I get Cv0 and Cp0? These are standard data that have been measured, and over a range of temperatures, these are given in various tables. So what is done there is that it says that Cp0 for this material is equal to this much for a temperature range from this temperature to this temperature. And it also will tell you that this is good enough within say plus minus 3% or 4%. And that's good enough for our purpose. We will follow this. Where 3% is not acceptable, we have to go for the full equation like this one. So these are available in various books, charts, and even on the web. And we can pick up, knowing the material, whether the temperature is then this, we can get the specific heat there and then use it in a problem solving. So that's half the story done for the ideal gas changing specific enthalpy. Now we ask, how do I calculate entropy change for an ideal gas? So this could be a process where there is a, say, irreversibility in a compressor, or there is a heating of a gas taking place, and we want to know what is the entropy change. Enthalpy change we got, now we want to worry about entropy change. So we have two options here. Entropy change can be obtained either from a combination of pressure and temperature, or specific volume and temperature. So we will get two equations, both are identical, and we can use either of them in our problem solving. So what we'll do is, first we will look at PT, then we will look at VT. So what we get with this is that TDS, we start with the relation that we already had. This is equal to DH minus VdP. One of the equations we have derived, the Maxwell's equations, as we were talking earlier. And now we do some simplifications on this. They're saying that DH, we have already just seen the definition of specific heat at constant pressure, can be written as Cp0 dt. And since it is an ideal gas, so remember this is now only for an ideal gas, V can be written as RT upon P. And so this gives us an equation which is Cp0 dt minus RT upon P, and there is a T on the left side. If you take it to the other side, we get an equation which says ds is equal to C0 dt upon T minus R upon P. No, sorry, into dP. And that is can be integrated. And to make life simple, we use Cp0, so this becomes independent of temperature. So when we integrate it, this comes out of the integral. And we do a simple thing from state 1 to state 2. And the answer is, we can just look at it and know that what it looks like. S2 minus S1. This will be integral of 1 to 2 Cp0 dt upon T minus R ln P2 upon P1. This term, there is no problem. It is straightforward. R is constant. We take it out, and that's what we get. And if Cp0 is constant, this final equation becomes Cp0 ln T2 upon T1 minus R ln P2 upon T1. And that is the equation that we have been looking for. We have an option of using some property data where a property called ST0 is listed in the tables, which is zero pressure standard state entropy, defined as T0 to T, Cp0 upon T dt. And S2 minus S1 will be then ST2 at the zero state minus ST1 at zero state, and we get the answer. Which means that you take the temperature, look up the table, get the value of this one. Then at this temperature, get this value, subtract the 2, you get S2 minus S1. But the caution is same, this is for 0.1 megapascal and at low pressure zone. So this is a quick way to get numbers. In some cases, these two numbers will be very close to one another. when pressures are very high, this may not be good enough to use. So for our purpose in this course, we expect that we will use this equation. That's good enough. Okay, so this is one thing. So I said that entropy change for the ideal gas can come from two parts, pressure and temperature. So this is pressure here, temperature here. The second formulation is temperature and specific volume, and we will look at that next. So here we have entropy change, but now we use a different equation. TdS is equal to du plus PdV. And here we make the substitutions as before. Du we now know is Cv0 dt, and T is RT upon V, the ideal gas equation of state. Again, this is ideal gas entropy change. And like before, we do that simple calculation, simplification, integration, and you get S2 minus S1 is Cv0 ln T2 by T1 plus R ln V2 by V1. And that's the second equation that we have been looking for. So now what we have got, we know how to evaluate change in specific internal energy for an ideal gas, change in specific enthalpy, and now we have equations for change in specific entropy, and that completes everything that we've been wanting for. So we are in now a good shape that knowing some state points, we can calculate all the other properties even for an ideal gas. We did not use any tables. For the non-ideal gas behavior, we use only tables. For ideal gas, we have these four relationships. Life becomes much easier when we look at all these things. Now I mentioned that Cp is a function of temperature. So let's spend a few minutes looking at this data, which is real data for substances. On the x-axis is temperature in Kelvin, starting from 0, 400, 800, 1200, 1400. On the y-axis, Cp in kilojoules per kg per Kelvin, and starts from 0 and goes up to 18. And what you see on this curve is that there are a lot of curves that are over here, in fact over here, one slightly above that, and this one way above that. That means here is a material whose specific heat is like 14 kilojoules per kg per Kelvin. It can take in a lot of energy for its temperature to rise by 1 degree Celsius. And this substance is hydrogen. So that's what we have. A very common substance. We can happily produce it by electrolyzing water, and it has this wonderful property of very large specific heat. So where does this come in use? That if you want to cool something, you would like to have a substance which can absorb a lot of energy and its temperature doesn't rise too much. Because otherwise then the differential of temperature between the coolant and the material will decrease, and the heat transfer rate will come down with the Newton's law of cooling, and that's not a very nice thing. So here is hydrogen, which has a tremendous specific heat, and that's why in large electric power generators in all power stations, whether nuclear or coal-fired or oil-fired, the cooling of the generator, which is like cooling an electric motor, which is generating heat because of I square R losses, that cooling is done by hydrogen. So all these big machines are filled with hydrogen to like 3 bar pressure, 4 bar pressure, and that is the reason why we use such a chemical, which actually is, from a safety viewpoint, is somewhat dangerous, but it's got excellent thermal properties. So this is way outlier. Hydrogen is way out on this chart. So let's now move on from there and Look at the next big chart that comes up way up here, and this is helium. So here is helium. Okay, so here is helium. And by looking at it, it looks like this line is almost straight. And that is the case. But as far as value goes, it is 5 point something, which is again a very high specific heat. So helium has nice high specific heat and is completely independent of temperature. That's what we see from this part. Now let's go down further in this. And with the last line here, this also looks pretty much straight. And if you see what this is argon. So argon specific heat doesn't change with temperature. Helium specific heat doesn't change with temperature. And you can extend that and come up with the thing that helium and argon are monoatomic gases. They have very little manners in which they can absorb energy in the atom. And so the specific heat doesn't change much with temperature. So these are two monoatomic gases. The dependence on temperature is very weak. Now let's look at all the other things that are lying in between here. We then have nitrogen there. You can see this nitrogen, the specific heat increases slightly as you go up. There is oxygen, which is the cross. You can see this is going up there. So what has happened now is that these are diatomic gases. They have vibrational modes of storing in energy, and so their specific heat is now dependent on temperature much more strongly, whereas monoatomic gases had nothing. Hydrogen was also a diatomic gas, so there is a slight increase we see there. So monoatomic gases, specific heat don't change much with temperature. Diatomic gases, somewhat strong dependence. And you go to bigger molecules, carbon dioxide and water, and this is a propane and R134A, which is a little bigger molecule, and you can see that they all have a dependence on temperature. But qualitatively, if you see, their specific heats, including that of water and even nitrogen and oxygen, are way below hydrogen, way below helium, and way below hydrogen. So there's a huge difference there. And this curve, which is, you can see this is for water, this is going up, and we can see that water in a liquid state that we know has a specific heat of about 4.18 kilojoules per kg Kelvin. And we know that water is one of the materials which has the highest specific heat amongst all known materials. That's another way why water is a good thing. Is firstly it is abundant, and second it is good for cooling. So water is 4 kilojoules per kg Kelvin, very good high specific heat. Metals, the specific heats are much lower, but when it comes to other substances, you have helium and hydrogen as two materials with very, very high specific heats. And this is good for engineers, whereas hydrogen is dangerous, so you have to be a little more cautious in designing your equipment. Helium is inert, and you can quite happily use helium and not worry about any corrosion or reactions. The trouble is, helium is it's a rare gas, very expensive. You can buy it, yes, but use it only if absolutely you must. So that's what we were looking at, integrating Cp with T. This is the gaseous phase. Okay, now we look at something that you have learned in school days, but it now comes out in 2 minutes by looking at what thermodynamics we have learned, and which is that what is the relation between the two specific heats. Okay, so we have this relation, the definition of specific enthalpy, dH is equal to du plus pdV. True for everything, no issues. Now we say, what about an ideal gas? And we say this dH will become Cp0 dt, du becomes Cv0 dt, and this becomes pdV becomes R dt. And you remove T from there, and you get Cp0 minus Cv0 is equal to R. It's something we have known from school days. Units of all three in SI units are kilojoules per kg per Kelvin. And the second thing, a number that we will now exploit more and more, for gases we do it, that is the ratio of Cp0 to Cv0, which is defined as K, or in some cases gamma, the specific heat ratio. And if you remember your physics from other courses, you see that for air it is 1.4, for monoatomic gases it's about like 1.67, for bigger molecules it is smaller. So that's something that comes up, and this K comes up in many applications that are there. So we have two more relations that we can use, that K defined as the specific heat ratio and Cp minus Cv0 is equal to R. So this came about from a very nice way. From the first law of thermodynamics, we defined this. Ideal gas approximation came this, then comes this. This is always true, but this is an approximate assumption that we made. So this relation is only true for ideal gases and for no other substance.